All right, good morning, good afternoon, ladies and gentlemen. Welcome to this series of online lessons. If you haven't already, subscribe, leave a like, and comment on this lesson. Now, in today's lesson, we're going to look at linear transformations. And basically, this is a linear algebra topic, linear transformations. So let's talk about transformations in general, okay? So transformation in general is just about having an object. So if this is an object, call it object. An object can be governed by a certain machine, and when it goes through that machine, it becomes another object. So for instance, it may become even a smaller object like that. We can say this object has been transformed. So this is the image. Okay, so there is an object, which is the original piece of object. When it goes through what we're calling a definition governing the transformation. So we say this is a definition governing a transformation. When this object goes through the definition that governs this transformation, it becomes an image. So this is what transformations are all about. Now, on these transformations, there are transformations that are linear and transformations that are not linear. I'll give an example of linear transformations that you may be aware of from grade 12 maybe, and so on and so forth. For instance, a translation. Translation is basically when an object is there and it goes to another point without changing the shape and so on and so forth. So that is a translation. Then you have magnification. So magnification is another example of a linear transformation. You have a reflection. Reflection is another example of a linear transformation. This is where an object is reflected like that, okay, using a mirror line like that. So those are examples of linear transformations that you may know. Now, there are cases where maybe you have an object like this and it goes through a particular definition, okay, and maybe it comes out something like that, okay. It goes through a definition and the shape that is produced here is maybe just something else. So this is an example of a non-linear transformation, okay. Now, in this topic, we are going to be looking at definitions given, okay. So like here, so there is a definition here governing this transformation, okay. There is also a definition here governing this transformation, and the definition here governing this transformation. What we're going to do is just determine if the definitions given are definitions of linear transformations, okay. So that is what this is all about. So we're just going to look at the definitions given and we consider if that definition is a linear transformation. Now, how do we do that? Okay, I think you should have written that, but how do we determine whether a definition given is a definition of a linear transformation or not? We need to know some things that are simple. So if T is a linear transformation or a K-morphism, if T is a linear transformation from an object to an image, okay, like that. T is linear, okay, so we'll say, let me write here, say T is a linear transformation. Basically, T transforms V into an object. Transforms the object V into an image W. T is linear, or T is a linear transformation. T is linear if, when you transform the vectors in V, that is U plus V, when you add them and you transform them, the vectors in the given object, what you get is the transformation of the individual vectors plus transformation of V. Okay, so for instance, if the object, so we need to identify the object and the definition of the object, and we decide that we find vectors in that object, and we transform the vectors, we add the vectors, then we transform them. If we get the same as transforming the individual vectors, okay, that is one condition satisfied for linear condition. Okay, there are two conditions that should be satisfied. The other condition is if you get the transformation of alpha times a vector in the object, what you should get is alpha outside times the transformation of that vector. Okay, so these are the two conditions. These are the two conditions that have to be satisfied for us to determine whether a given transformation is linear or not. Okay, so these have to be satisfied. If one of these is not satisfied, we conclude that the transformation is not linear. Okay, so let's look at an example, then we progress from there. All right, so we have this question here. So is T that maps a polynomial in 3 dimensions onto a 2 by 2 matrix defined by, so you have a polynomial there, and what you get is a 2 by 2 matrix, a linear transformation. Is this transformation a linear transformation? So for us to prove that this is a linear transformation, first of all, we need two vectors. So we'll let two vectors U and V be elements of the object. So always they have to be elements of the object. So in this case, there will be elements of P3, meaning that U will be equals to some polynomial like it has been stated here. So we are following this definition here. So if this was a vector, say U comma V, then U would be U comma V. But in this case, we have constants like that. So we can say alpha 1, then plus B, plus alpha 2. Let me use alpha 2x. Okay, plus another constant alpha 3x squared, plus alpha 4 x to the power 3. So we let U be equals to that, and we also let V be equal to a similar vector. We have constants like this, and basically we're going to beta, so beta 1 plus beta 2x plus beta 3 x to the power 2 plus beta 4 x to the power 3. Okay, now after letting these two vectors be part of the object, what we just need to show is that when you add the transformation, or when you add the two vectors, which is U plus V, what you should get is the transformation of the individual vectors. Okay, and secondly, when you multiply a given vector with an alpha, say alpha times u, what you should get is we can factor out this scalar alpha and get the transformation of u. Okay, so having that said, we firstly need to transform each of these vectors separately. So we need to find transformation of u and transformation of v. Okay, so transformation of u, we'll be getting the vector u like it is, then we use so transformation of u, we get the vector u as it is, which is alpha 1 plus alpha 2 x plus alpha 3 x to the power 3 to the power 2 plus alpha 4 x to the power 3. Okay, and when we transform this according to the definition, so this is the definition. So according to the definition, the entry here should be this times the coefficient. So the constant times the coefficient of x. So in this case, the constant is alpha 1 and the coefficient of x is alpha 2. So the entry here will be alpha 1 plus alpha 2. Okay, then the entry here should be the constant minus 2 times the coefficient of x squared. So the constant, which is alpha 1, minus 2 times the coefficient of x squared, which is alpha 3. Okay, minus 2 times the coefficient, which is alpha 3. So we're just following this definition. Then the entry here should be d. D is the coefficient of x to the power 3. So the coefficient of x to the power 3 is alpha 4. So we'll put alpha 4 here. Then lastly, this should be b minus d. B is the coefficient of x and d is the coefficient of x to the power 3. So b is the coefficient of x, which is alpha 2 in this case. The coefficient of x is alpha 2 and the coefficient of x to the power 3 is alpha 4. So we've found our transformation of u. So I was basically going to write it here. So this is a transformation of u, which is equals to this. Now we need to find the transformation of v as well. Okay, so what is the transformation of v? Transformation of v will be getting the vectors in v, which is beta 1 plus beta 2 x plus beta 3 x to the power 2 plus beta 4 x to the power 3. Okay, and when we do the same, when we transform, we're going to have beta 1 plus beta 2, then beta 1 minus 2 beta 3, beta 4. Then here we're going to have beta 2 minus beta 4. Okay, so that is what you're going to have, minus beta 4. Okay, so these will be your transformations. Now you have your transformation of u and transformation of v. Now we can start proving. Okay, so now the first thing that we're proving is transformation of u plus v. So the first thing that we're proving is that transformation of u plus v should be equal to the transformation of u alone plus the transformation of v. So the first thing that we're going to do is we're going to get u plus v. So we'll say transformation of, we need to write u, which is this that is inside here, that is our u. Okay, then we add it to v. Okay, now I'm going to do this addition systematically. We're going to just add from here so that we write the answer here. So it will be alpha 1 plus beta 1. So it will be alpha 1 plus beta 1. We're just adding the the like parts. Then here we're going to have alpha 2 and beta 2, then we'll factor out the x. So we are just doing the simple addition. So this is plus alpha 1, alpha 2, sorry. So alpha 2 plus beta 2. And since both of these have x, we'll factor out the x. Same applies here. We're going to have alpha 3 plus beta 3. So plus alpha 3 plus beta 3. And since they all have x to the power 2, we'll factor out x to the power 2. X to the power 2 plus the other one is alpha 4 plus beta 4. And again, since they have x to the power 3, we'll factor out x to the power 3. Okay, so this is u plus v. So this is u plus v. So we've gotten u, which is basically just this vector here. So we've gotten u and v, and we've added this. So the addition is basically this times this plus this, this plus this, this plus this, this plus that. And we factor out the like terms and we get this that is here. Then now we need to transform this. Okay, so we need to transform this this given equation here. So according to the transformation, so we follow the definition. So we follow the definition. So according to the definition, the first entry here is the sum of the constant, which is alpha 1 in this case. Let me just erase that. All right, so according to the definition, we are getting the constant, which is this one, plus the coefficient of x. Okay, so in this case, the constant is this, then the coefficient of x is this. So it would be alpha 1 plus beta 1 plus the coefficient of x, which is alpha 2 plus beta 2, alpha 2 plus beta 2. Okay, so that will be the first entry here. Okay, then the second entry here is saying you should get the constant, which is alpha 1. So here the constant is alpha 1. In this case, the constant is alpha 1 plus beta 1. Then you subtract from 2 times alpha 3. Okay, alpha 3 is the coefficient of x squared, and in this case, the coefficient of x squared is this. So we get the constant. In this case, the constant is this, minus 2 times the coefficient of x to the power 3, x to the power 2, and in this case, it's this. So it will be alpha 1 plus beta 1 minus 2 times the coefficient of this, which is this, alpha 3 plus beta 3. So alpha 3 plus beta 3. Okay, then now we come to the other entry. The other entry here is alpha 4. So alpha 4 is the coefficient of x to the power 3. So the coefficient of x to the power 3 in this case is this right here. So that will be right here. So that will be alpha 4 plus beta 4. Okay, now this entry is alpha 2. Alpha 2, okay, so we are basically following the definition. So alpha 2 is the coefficient of x. So in this case, the coefficient of x is this, and alpha 4 is the coefficient of to the power 3 of x to the power 3, and in this case it's this. Okay, so that is, so this minus this, so that will be our fourth entry there. So it would be alpha 2 plus beta 2 minus alpha 4 plus beta 4. Okay, so now after doing this, you need to simplify. So we basically group the alphas alone and the betas alone. Okay, so in this case, here the alphas alone, it would be alpha 1 plus alpha 2, then plus beta 1 plus beta 2. Then here this will be alpha 1 plus beta 1. Then we distribute this. This will be negative 2 alpha 3, negative 2 beta 3. So here, this is what you always do. You group the similar parts. So in this case, you group alpha and alpha. So it will be alpha 1 minus 2 alpha 3 plus beta 1 minus 2 beta 3, like that. Then we go here, so this is already grouped. So this is alpha 4 plus beta 4. Then here this will be alpha 2 plus beta 2. Then this will distribute as negative alpha 4 minus beta 4. So this will be written as alpha 2 minus alpha 4, the like terms, plus beta 2 minus beta 4. Okay, so this will be the transformed matrix. Then from here we can group, so we can ungroup by addition. So this can be written as the sum of alpha 1 plus alpha 2, then alpha 1 minus 2 alpha 3. Then here we have alpha 4. Here we have alpha 2 minus alpha 4. Okay, then the other part will be plus the betas. It will be beta 1 plus beta 2. Down here we're going to have beta 4. Then here we're going to have beta 1 minus 2 beta 3. Down here we're going to have 2 minus beta 4. Okay, so now this has come from the fact that in matrix addition, you add the values correspondingly. So it's this plus this, which will give you this. This plus that, which will give you that. This or this plus this, which will give you this. This plus that, it will give you that. And when we check, these are actually equal to the transformation of u, which is this part. So transformation of u, let me just put it here. So transformation of u is actually equal to this, and the transformation of V is equal to this. So we see that what we get here is transformation of U plus transformation of V. So meaning that the first condition has been verified or has been satisfied. Then now from here we need to go to the second condition. Okay, so first condition has been verified. We go to the second condition. So the second condition, the transformation of alpha U should be equals to alpha transformation of U. So what we're going to get is, we just need to get a scalar alpha, which is any scalar of the K space. We multiply it with the vector U. So first of all, let's say, okay. And we'll take the transformation of that. Okay. So we say alpha times the vector U, we see that we're going to have alpha times the polynomial alpha 1 plus alpha 2x plus alpha 3 x to the power 2 plus alpha 4 x to the power 3. Multiply, we're multiplying across. So this becomes T of alpha 1 plus alpha 2 plus alpha 3 x to the power 2 x, then plus alpha 4 x to the power 3. Okay, then we'll perform the transformation. So we are referring to this transformation here. Okay, that is the constant plus the coefficient of x. So this was the plus here. Okay, so the constant is b, and the coefficient of x in this. So here the constant is this, so that is alpha 1 plus the coefficient of x, which is this, so which is alpha 2. Okay, then we look for the other entry here. So down here it should be b4, and b4 is basically the coefficient of x to the power 3. Okay, x to the power 3. So in this case the coefficient of x to the power 3 is alpha 4. Okay, then we need two more entries. The entry here is the constant, like this. So the constant minus 2 times the coefficient of x to the power 2. So the constant, which is alpha 1 in this case, minus 2 times the constant of x to the power 2, which is alpha 3. Okay, we go to alpha 2 minus alpha 4. So alpha 2 is the coefficient of x, and alpha 4 is the coefficient of x to the power 3. In this case, the coefficient of x is this, and the coefficient of x to the power 3 is this. So this will be alpha 2 minus, is it a minus? Minus alpha 4. Okay, minus alpha 4. Then what we're going to do is, we see that alpha here is appearing everywhere. So we see that there's the alpha. So we can basically just factor it out. So we can factor out the alpha. So this will be equal to the alpha factored out. And what we'll remain with is a matrix that has alpha 1 plus alpha 2. Then here we have alpha 1 minus 2 alpha 3. Alpha 1 minus 2 alpha 3. Then here we have alpha 4. Then here we have alpha 2 minus alpha 4. So when we see this is basically transformation of U. So transformation of U, which is right here. So when we compare, you just find that this is actually equal to the transformation of U, which is this. So you just say this is equals to, there is an alpha here, then there's a transformation of U out here. So meaning that the second condition has also been verified. So transformation of alpha U is equals to alpha transformation of U. So you need to make a conclusion when the two conditions have been verified. So you say, since transformation of U plus V was equal to the transformation of U plus the transformation of V, and transformation of alpha U was equals to alpha transformation of U, TP3 that maps onto a matrix in 2 dimensions is a linear transformation. And that will be it. So let me give you some questions and just see how you will approach them. Then we'll move on from there. Okay.